So in this lecture, we will learn some skills which are essential for, let's say, any data analysis, which is fitting models to data. And to do so, you will have to use most of the techniques that JCK and I have taught you over the previous lectures. So, for example, the simplest way of fitting a model is a linear model. That is, you fit a line to two dimensions of points. And so we also have, you'll notice that I have NumPy here to handle the arrays. I have SciPy here to actually do the regression, and then I have Matplotlib to allow me to visualize this. What I'm going to do is first, I'm going to generate some random numbers just to illustrate to you how these fits are done. So I'll say np.random.random10, and y is also np.random.random10. Now, notice that because I'm calling a random number generator twice, even though it looks like x and y should be the same, x and y will be just two arrays of length. So yeah, let's just examine what's in x. Yeah, x and y are two arrays of length 10. Now I will visualize this by doing enter x comma y. Right, these points are all over the place, and should you fit a line to it? Perhaps not, but let us see what you will get if we do and how to do it. So to fit lines to data, the function to use is, we have already imported SciPy as SP. So, I mean, there are multiple functions you can use in Python to do fits, but this is one of them. sp.stats. Why is it? Okay, so maybe just so that I can have the interactive thing on, I'm going to import from SciPy import stats, right? Because Collaboratory's interactive facility does not go more than one library, one sub-library deep. So let us now look at dot. Yeah, so notice that, yeah. So it is telling me that there is a function within stats called linRegress. This is a help that has popped up on its own in Collaboratory, and it takes x, it takes y, and it returns 2, 3, 4, 5 numbers which correspond to slope, intercept, R value, P value, standard error equals x comma y. So let's now see what that does. If we equal stats.linRegress x comma y. So let us now examine what the slope is. So what I mean by a slope is that you can in principle write any line in coordinate geometry, that is Cartesian coordinate geometry, as y equals slope times x plus y intercept, right? So now if x has the value of 0, then the value of y is your intercept. So this is the point at which the line intercepts the y-axis, and so we will see exactly what this is. So I am fitting a line of this shape to these data points, and I'm getting a value of slope equals 0.15, and intercept equals 0.4. Let us visualize this to allow us to judge if this is actually a good fit. And to do that, what I'm going to do is I am going to dot linspace 0, 1, 100. So what this tells NumPy is to generate an array between which contains the numbers between 0 and 1 with 100 intervals in between them. So by doing that, we can examine what this array contains. XPL. Yeah, you notice that this array, the lowest number is 0, which is what I gave here. 1 is the highest number, which is what I gave here. And it contains in total 100. It is a 100 length, and it is the spacing between all the numbers is equal. Now, what I'm going to do is I'm going to, because I told you this is the shape of the line, y equals slope star x plus intercept. I'm going to do ypl equals, so these are arbitrary names I'm picking just to plot, equals slope star xpl plus intercept. I'm calculating this for the array. Now let us plt.scatter x comma y, which are the same points that I already plotted, and I will do plt.plot xpl comma ypl. Let us examine what has happened. You will notice that the best fit line for all of these points looks like this. And quite obviously, this is not, it is not very illustrative. Perhaps to be more illustrative, what we shall do is we shall generate x equals np.random 25 and y equals 12 star x plus 5 star x plus 14 plus np.random 25. Now, if I do this and then I plot these line points, you see that they actually look like a line. The amount of scatter you see around a line is because I put in, I added to each number. So here I want you to understand what I did in these lines. Now I generated 25 random numbers between the value of 0 and 1. To each of those numbers, I am assigning its y coordinate, which is according to this equation, slope plus intercept, 12.5 plus 14. So 14 is the intercept, 12.5 is the slope. And I'm also adding some noise, which is 25 random numbers between 0 and 1. But you notice that because this is always between 0 and 1, and these numbers are much larger, the noise is quite small. And so if I plot it, I get something that looks like a line. Now let us examine what a linear regression on this does. And you will notice that, let us now examine what the slope is. It's 12.09, which is very close to the 12.5 I put in. The difference is only because of the noise I have added. And if I check intercept, it will be close to, it is 14.74, which is again close to the 14 intercept that I put in. The difference is only because of the noise. So now if I plot this again, let us examine what it will look like. So yeah, you have these points, and then you have the best fit line for it. So you may wonder what R value, P value, etc. are. And the only way to know that actually is usually for an arbitrary function to actually read the function's documentation. If you have Matplotlib, if you have Collaboratory or Jupyter Notebooks, you can read the function's documentation like this straight away. Otherwise, you can just type out the function scipy.stats.lin regress out into Google, and usually the first thing that comes is the documentation for a function. And so this is how you look up how a function works. And once you have that figured out, you understand what those things are. So once again, notice that it returns the slope, the intercept, the R value, which is a correlation coefficient. So a fit like this is usually performed by minimizing the distance between the points and the line. And that is usually called R square. And the smaller the R square is, a better fit it is. And then the two-sided p-value corresponds to a way to test the statistical hypothesis that the slope is 0. And if you examine the p-value here will be very, very small. It will probably be 1 in a billion or something. Let us examine that. See, it's actually much smaller than 1 in a billion, and that's because this fit is so good that you can reject the hypothesis that the slope is 0 to a very large confidence interval. In fact, if the slope was 0, you would get points that are this correlated only 1 part in 10 to the power 25, which is a very small number. Now, just to illustrate exactly what I have done, I'm going to remove this noise, right? Just to show you what are the ingredients that go into this fit. So now the points I'm using, they're perfectly correlated, as you can see, because there is no noise. I am literally using the exact expression for a line. And now if I do a fit, let me check what the slope is. You see that I get 12.5. I mean, this is 12.499, whatever, many 9s and a 6, but this is as good as 12.5. So computers are at finite precision, and sometimes they do things like this. This will usually be rounded up to 12.5. Now, if you examine what the intercept is, again, you'll probably get exactly 14, which is the intercept that I put in. So now if I can plot this again. As you see, the line that I produced using the fit is a perfect fit for the data points, but that's only because I generated the data points using this line. The important thing to remember here is that any line in 2 dimensions can always be expressed as y equals mx plus c, where m is the slope and c is the intercept. This is, even if this is 10 standard or 12 standard coordinate geometry, even if the line is of the form ax plus by equals c, you can, of course, divide everything by a, and you can get it, you can divide everything by b, and you can get it to be of the form y equals mx plus c, right? So in this case, this is how you perform a linear regression. the other things here, the R value, the P value, and the standard error, these are concepts you will understand as you perform more and more fits. I think an important thing to move on after to understand after you perform a linear fit is to see what happens if you fit a polynomial. So let us once again do x equals np dot random of 25, y equals np dot random of 25. Now I have two new arrays of random numbers. I am going to just plot it to visualize. Scatter x comma y, and you can see that it's all over the place. So now we will progressively fit more polynomials, a polynomial of higher order to the problem using numpy.polyfit. So let us examine what np.polyfit, how polyfit works. I do not know this off the top of my head, so I am going to examine the function. Right? So what it takes is, it takes x, y, and it takes a degree. Now, if it returns a shape of degree, an array of shape degree plus 1, and the residuals. The residuals are the I will explain to you what those things are. So let us now fit x comma y comma deg equals 1. So this should give us the same as a line, but rest equals. Now, let us examine what is contained in res. It is an array of length 2. That is because I gave it a degree of 1. So now let us try xpl. We already have xpl. Ypl equals xpl star x of 1 plus, xpl star x of 0 plus x of 1. I believe this is the way to go about it. Now let us try plotting this. You notice that this is again not a good fit, but maybe we shouldn't fit a line to this. We should fit a second degree polynomial. So what we should do now is so in this case, now it is a curved line because it is a second order polynomial. Maybe it is a slightly better fit. What we shall do is we shall now go to arbitrary lengths and see what it will do for us. So to do that, I am going to use a for loop because I need to. So I will use YPL equals XPL star 0. Watch what I do carefully, and I will explain it to you multiple times after this. For I in res. So YPL equals YPL plus XPL star X star. Okay, I should have used, no wonder I was producing, I had a mistake earlier. I should have used res here. So let me see this now. Is this a better fit? Nope, let me understand what's going on. So this is polynomial fit. It returns the highest power first. So rest of 2. This is what I should be using. Okay. Yep. Okay, so this is how the fit works. I'm going to use a for loop to do this because was now let us try it this way. So now I'm fitting a 1 degree polynomial, which this will fail, of course. So what I should do is of 0 plus res of 1. And if I see how that works, yeah, this is what a 1 degree polynomial, which is a line fitted to the same data, looks like. If I want to fit a 2 degree polynomial, let me try using this. So just to be just to verify that I'm not making a mistake, I am going to now do fit. Oops. So there appears to be a bug in how I'm doing things. Let me understand this. So So on my first loop, I am adding to it but okay, so this is what I should do. This should be, yep. So just to explain to you what I have done now, let us do 25 now. So I'm generating 25 random points, and as expected, they're scattered all over. If I fit a 2-degree polynomial to it, the fit is probably not that great. It's somewhat okay. But let me try and fit now a 25-degree polynomial to it, since there are 25 points. Or 24-degree polynomial, because there are 25 points. And what I can do is, you see, I got the points go through. Let us now try fitting, for example, a 22-degree polynomial. Yeah. So let me explain to you what we are doing. If you check the polynomials, I have to turn this into text. So any polynomial can be written as y equals a star x plus b star x to the power 2 plus c star x to the power 3, etc., all the way till how many ever orders you want to, plus z plus a y-intercept. So if it is a line, this is your intercept, this is your slope, and these terms don't exist because it is a line, and lines have only one order. But you can, and a polynomial of arbitrary order has these many terms. Now, your function polyfit tells you that what it returns is the polynomial coefficients, which means that it is giving you the values of the coefficients a, b, c, etc. And the highest power is first. So when I want to evaluate a polynomial of a given shape, what I need is I need to raise it x to the highest power when I'm examining res with. So now I'm going over all values within the res array, which is something returned by this function, which contains the coefficients of all the polynomials. And I am progressively adding the higher order, the terms. I start with the highest order. So in the case of a 22nd degree polynomial, I am starting with x raised to 22, which, as you can see, is power in the first iteration. So the output you see here is the output from this line. So in the first iteration, I am adding x raised to 22 multiplied by res of 0. In the second iteration, I'm adding x raised to 21 multiplied by res of 1. I'm going all the way there, and then I'm going to res of 22, and I'm adding x raised to 0, which is 1, multiplied by res of 1. So you can see that this allows me to evaluate the value of a polynomial, and that polynomial, so just to, maybe the fits are not so nice to see because of the unconstrained extremes. So let us try what a 15-degree polynomial would look like. You see, it tries to go through all of these points equally. Now, the thing to note is that if you have 2 points, you can fit a line to it. If you have 3 points, you can fit. So, if you this is again simple geometry to understand, coordinate geometry. So, if you have just 3 points, like this situation, then the maximum you can fit is a second-degree polynomial, right? And you will see that it is okay. If I plot now, it has fit a second-degree polynomial to the 3 points I generated. You see these 3 points. But if, on the other hand, I try to fit a third-degree polynomial to 3 points, it will complain that it is poorly conditioned. And this is because we know that if you have less number of points than the degree of the polynomial you're trying to fit, the underlying matrix is singular, as in it is not a well-defined fit. You cannot do that, which is why it is complaining. So let us now examine, for example, a case of 8 points, right? Just to illustrate this better. And you see I have 8 points here. I can fit a 3D polynomial to this. And you see it is not a very good fit, but it is able to do a fit. I can fit a 7D polynomial to it. If I were to do that, let's examine what's happening. And you see it goes through every point exactly. If I were to fit a 6D polynomial, you notice that here it is taking some liberties, like it is going between the 2 points, but it fits almost all the other points perfectly. So yeah, this is how you fit polynomials to data using NumPy and SciPy. At this point, I'm going to pause and ask you if you have any questions about what I have explained so far. If not, we will move on to using splines, to doing interpolations, etc. But yeah, does anyone have any question? If you do, please raise your hand. Everyone's perfectly clear on what exactly I have done? You understand the for loop I wrote to evaluate what goes into plotting this line? Okay, excellent. What we are now going to do is we are going to look at certain ways to interpolate between data. And for that, again, there is multiple tools within Python. So I think one of the things is scipy.interpolate or numpy.interp. These are both, I think, pretty much the same thing. But let us look scipy.interpolate interp 1D. So import interpolate. So once again, if I give you a sequence of data, now I have these many data points, and so plt dot scatter x comma y. The question is, if I want to know what is the best fit value of the y-axis to an x-axis point that I give you, how do you interpolate between these data points? And you may find that by creating an object called interpolate.interp1d. So let me create this object as interpolate.interp1d. Let us examine what it does. So x comma y, right? Now, the thing to understand is, now if inter is a function. Now, if I evaluate inter at 0.5, let us understand what it is. It will give me a value of 0.8. What this is telling me is that this interpolating function has a value of around 0.8 at a value of x coordinate of 0.5. You may not find it particularly useful right now, but I can do xpl. So this is, I'm making this to plot, and p.linspace 0, 1, 100, and ypl equals inter of xpl. Let us evaluate this. Ooh. Of course, this should be an integer, and I was giving it a float, and it can't convert. Oh, come on. Below the interpolation region. Of course, 0.1, 0. Okay. So does numpy left equals 0, right equals 5? I just need to specify. I'll explain to you what exactly I'm doing. Right equals 1. Let me create this word. Of course, sci-by.interpolate. Fill value. Yeah, I'm going to do something which let's try this. Cool. So now let me try plotting. Yeah, you may see that. So just to illustrate this point better, I'm going to do this. So I hope you can see what has been done. You have a set of points which specify this object called your interpolator, and I am giving it these set of points, and I'm also telling it that outside the range of those points, just extrapolate. And now I essentially have a function which at every point is determined by a line that is defined by the point that is right just to its left and just to its right. So this allows me to interpolate between any sets of values. And you notice that your interpolating function now looks like this if I visualize this. So I'm going to pause and ask you if you have any questions. Do you have any questions about this interpolation? You understand this perfectly, what I'm doing? Excellent. So you understand interpolators. Anyway, all you can do is you have to take this exact notebook that which I will share with you, and you can try varying these numbers. You can play with it. Only experience can teach you. As you can see, I'm also making mistakes, and I am figuring this out on the fly. So that is how you can do this. I will now teach you a better way to interpolate data called a spline. So let us do this with spline. Yeah. So scipy.interpolate also has an object called cubic spline. So let me show you what that does. So CSPL equals interpolate dot q. Why is it showing only cubic Hermite spline? Yeah, it's showing also cubic spline x comma y. IPL equals CSPL of XPL. So, okay. This is, of course, this is because X. Now let us examine what this looks like. You notice that I am creating these points from scratch again, so it will look quite different from this figure. Yeah, so, if I were to, because this should be an integer, which is why it's complaining. Now, let us examine what this will look like now. Yeah. So a cubic spline is another way to interpolate between data, but in such a way that each section of the data are not fit by a straight line with jagged edges, but that it is always smooth. You'll notice that unlike in the case of your linear interpolation or one-dimensional interpolation, which is what is interp 1D. Here, each session between each 2 points is represented by a cubic polynomial in such a way that the 2 points plus the condition that its slope with respect to the next session of the cubic polynomial has to be continuous are used to constrain the polynomials, and then you get this cubic spline. So these are different techniques used to fit and project and interpolate data. Polynomials interpolation, yes. And as you see, these are all from SciPy interpolate package. So there are multiple different types of splines. Those of you who have done some engineering might be aware of things like Hermite splines, B-splines, etc. Or also you can have polynomial splines of higher order, cubic being the third degree case. There are, I believe, also quadratic splines. And you will find all of these in scipy.stats. So for example, you can just type this out and you see literally every kind of function that you ever want is there. And it's a question of looking through each of them and understanding what each of them mean. So do you have any questions about linear regression, fitting, interpolation, or splines? Let me... No questions so far? Okay, so yes, Modish. Sorry, I asked someone else to unmute. Hi, Modish. I've asked you to unmute. Yeah.
Hello, sir. Good afternoon, sir.
Good afternoon.
Sir, I don't know the meaning of spline, sir. I haven't done this. So
okay.
I've done best fit line or other things.
Sure.
But spline I haven't done. Yeah.
So a spline is a tool used to make. So you understand some amount of differentiation, right? Calculus.
Yes, sir. Yes. Differentiation and calculus. Yes.
Okay. So you have a set of points, and you want to draw a function through the set of points. If you use as a linear interpolation, then you get a function that is continuous, but but its first derivative is not continuous. Do you understand that? Because it has these jagged edges. It's not smooth.
Okay.
Now, if you want the first derivative to also be continuous, what you can do is, to each of this section, instead of fitting a line, you can fit a quadratic expression that is a second degree polynomial. And so to constrain a second degree polynomial, you need not just you need 3 data points, not 2 data points. So then you can use the 2 points and the condition that the polynomial you're fitting here and the polynomial you're fitting here should be continuous and differentiable, right?
Okay.
You can force that. And so a spline is a way of fitting. So every time this, and you do that with a quadratic, then what you get is your first derivative is, your line is continuous, but your first derivative is not. If you use, your line is continuous, your first derivative is continuous, your second derivative is not if you use a quadratic polynomial. If you use a cubic polynomial, then you get a cubic spline. And what happens is your line is continuous, your first derivative is continuous, your second derivative is continuous, but your third derivative is not at these points. And it's just a question of how smooth you want your function to be, what you're using it for. At this level of programming, I'm only teaching you how to use these functions within SciPy to get these objects. The examples I'm using, because I'm not putting too much thought into, generating data. So you notice that I'm always just generating random data. I'm not putting enough effort into making sense with these, like how to decide when to use a cubic spline instead of a linear interpolation. I'm not teaching you those things. I'm just showing you that SciPy has these features. In the work session on Wednesday, I plan to we will open a data set. We will do a bunch of these things. We will do a fit. We will do an interpolation. There we can see, depending upon the situation, whether you should use a spline or a linear interpolation, etc.
Okay, sir. Okay, then we'll ask question in that session.
Okay. Does anyone else have any questions? Right. What I'm going to do is I'm going to save this notebook, and I'm going to give it to Dheeraj, who will post it on the platform. I would strongly recommend that you download it, play with other functions, try variations of all the things that I have shown you. Even though this was supposed to be a 1.5 hour class, the things I intended to teach today, I'm done with it. Because I'd kind of assumed that when I write a full for loop to teach you how I'm doing a polynomial fit, etc., you would have a lot more questions, or I would have to repeat myself. But so far you have not done that, so I think we're done for today. If you have no further questions, then I will end this call. Is that okay? Or does anyone want to raise their hand to ask another question? Okay, so I'm going to end this call, and I'm going to share the notebook with Dheeraj. I would strongly recommend you guys play around with what I've already done. Thanks.